Hello friends. Friends, today we will discuss a very important article, that is Einstein mass energy relation. We will discuss the meaning of Einstein mass energy relation, we will derive this result, and we will discuss the example of this relation. Okay, let us start with the discussion. Now, there is a very famous relation that is known as Einstein mass energy relation. What is this relation? This relation is E is equals to mc square. Now, what is the meaning of this E is equals to mc square? What is the meaning? The meaning is, you must have heard that energy can neither be created nor be destroyed. Okay, so it means that if energy neither be created nor be destroyed, then it can change its form to mass. Okay, or mass can be changed into energy. Okay, energy can be changed into mass, okay, with a multiplication factor of c square, and mass can be changed into energy with a division factor of c square. So c square is a common factor here. Okay, so we have to derive this result. Now consider an object of rest mass m0. Now what is the meaning of rest mass? That is whose mass is not changing. Whose mass is not changing. Okay. Now if force F is applied, if a large amount of force F is applied to the object such that it starts moving with a relativistic velocity. It starts moving with a relativistic velocity. Now what is the meaning of relativistic velocity? I have discussed in previous lectures. Please see the playlist of the relativity. The relativistic velocity means that the velocity of this object will be comparable to the speed of light c. Okay, so if the force F is applied such that the object starts moving with a relativistic speed velocity, that means the velocity is very high and comparable to the speed of light, then in the last article we have discussed about the variation of mass with velocity, that is m is equals to m naught divided by root of 1 minus v square by c square. So m is the variable mass, m naught is the rest mass, okay, and v is the velocity of the object. Now this will be our equation number 1. Now suppose that work done due to this force, will be dw, okay, and if the object is displaces along x-axis, then by definition work done is force into displacement, okay, F into dx, okay, and by Newton's second law, F equals to rate of change of momentum. By Newton's second law, F is equals to dp by dt, where p is momentum. So dw is equals to f dx. Now put the value of f in this equation. So dw will become dp by dt dx, okay, or dw is equals to d by dt mv dx, because momentum equals to mass into velocity. Now differentiate right hand side term, okay, differentiate right hand side. So dw will become m dv by dt plus v dm by dt dx. Now according to you, it may be come in your mind that the differentiation of dm by dt is constant because mass is not variable. But remember, here mass is also variable. Okay, m naught is the rest mass, m is the variable mass. So differentiation of m with respect to t will not be 0. So it will become dw is equals to m dv dx by dt plus v dm dx by dt. Okay, so or dw equals to mv dx by dt will become dv dx by dt, sorry, this one m dv dx by dt will become v dx by dt will become v, so mv dv plus v square dm, equation number 2. Equation number 2. Okay, now cross multiply equation number 1, this equation, cross multiply equation number 1, square, first square, or you can square again and square, okay, or square equation number 1 and then cross multiply is one and same thing. So it will become m square 1 minus v square by c square equals to m naught. Okay, you have to do square equation number 1, square equation number 1 and cross multiply. Okay, it will become m square multiply 1 minus v square by c square, root will be removed, and m naught square. Okay, and m naught square. Okay, or this equation will become m square c square minus v square by c square equals to m naught square, or m square c square minus m square v square equals to m naught square c square. Okay, now again differentiate this equation. Okay, now this equation will become c square 2m dm. What will be the differentiation of m square? Okay, it will be 2m dm. Okay, minus m square 2v dv minus v square 2m dm. Okay, what will be the differentiation of m square? Okay, 2m dm, m square v square, because both are variable here, it will become m square 2v dv and then v square 2m dm. Right hand differentiation will be 0 because m naught is constant and c is also constant. Okay, so it will be, right hand side will be 0. Okay, or this will become v square dm plus mv dv equals to c square dm. Equation number 3. Now compare equation 2 and 3. Compare equations 2 and 3. What is equation number 2? dw is equals to mv dv plus v square dm. Okay, so mv dv plus v square dm. Okay, equation 2 is mv dv plus v square dm, and compare equations 2 and 3. Compare 2 and 3, it will become dw equals to c square dm, equation number 4. Okay, now the total amount of work done by the applied force, this is the small amount of work done. Now the total amount of work done by the applied force in order to change its velocity from 0 to v, or from rest mass to a variable mass, will be achieved by integrating the left hand side of the following equation with limits 0 to w. Okay, so initially the work done is 0. When the work done is 0, the mass is rest mass. When the work done is w, the mass will be variable mass. Okay, so it will become w equals to c square m limits m to m naught, w is equals to c square m minus m naught, m minus m naught. Okay, this was our equation number 4. Now this will become our equation number 5. As this work W is done to give motion to the object, because when we are applying force F, then work done will be there, and due to this work done, object will start moving, and this work will appear in the form of kinetic energy. Okay, this work will appear in the form of kinetic energy. Okay, this is known as the relativistic kinetic energy. Relativistic kinetic energy. Okay, so we have to derive the total energy. We have to derive the total energy. E is equals to mc square, and we have derived the kinetic energy. Now our aim is to derive the potential energy. Now by definition of potential energy, or in the case of relativity, it is the rest mass energy. It is the rest mass energy. It is equal to the internal energy of the body. It is equal to the internal energy of the body or object. It is also equal to the work done to bring all the particles which make the object of rest mass m naught. Okay, suppose you want to make a bench. Okay, a school bench. Okay, now first you will collect all the pieces of wood. Okay, and then assemble these pieces to make the bench. Another example is, for example, you want to make a decorative item. Then you will collect all the relevant pieces and make a decorative item. Okay, therefore the rest mass energy of the body is derived. It is derived by integrating this equation. This equation was dw is equal to c square dm. Okay, now here the work done is from 0 to w, but it is the internal work done, to assemble a body. Okay, now in this case what will be the lower limit and upper limit of the right hand side? Lower limit and upper limit of the right hand side. Initially there is no object, 0, work done is 0. Then you collected all the particles and make an object, but that object is not moving. Then the upper limit will be m naught. So it will become w is equals to c square m naught. Okay, this work done will appear in the form of rest mass energy, that is m naught c square. Remember, the kinetic energy is due to the when the object is there having rest mass m naught, and you apply force and mass becomes m. Potential energy is there when there is no mass and you collected all the particles to make a mass. Okay, 0 to m naught. So in this case it is known as rest mass. So total energy will be kinetic energy plus rest mass energy. So put equations 6 and 7. So it will be m minus m naught c square plus m naught c square. Okay, so it will be mc square minus m naught c square plus m naught c square. So this will cancel out. So E is equals to mc square. So this is a famous energy mass relation, Einstein energy mass relation, Einstein mass energy relation. Here m is the variable mass. Okay, now this equation represents the The significance is that, or the importance is that, this equation represents the energy can neither be created nor be destroyed, but it can change its form. Okay, now there is example of this. There is example of this relation. Okay, that example is known as pair annihilation. Pair annihilation. Now, annihilation means destruction. Annihilation means destruction. Okay, whenever electron and proton they combine, do you know what will happen? We will get photon. We will get photons, gamma particle. Now, electron has mass. Okay, positron has mass. Does photon, with gamma particles, photons possess mass? No mass. Okay, but it has energy. Okay, so mass is converted into energy. Its opposite reaction is also there, that is known as pair production, where gamma particles are changed into electron and positron. Pair production, there is production in pair. Energy is changing into mass. So dear friends, this is all about the Einstein mass energy relation, the meaning and the example. If you have any doubt, please share in the comment section. Thank you. Thanks a lot.